reaction with our conjugated double bonds we're going to look at is not a new reaction. It's addition reaction to a double bond, but we're going to look at how many different products form when we have conjugated double bonds. Now, technically, this reaction can be done with more than just two conjugated double bonds, but it becomes more complicated. So we're not going to look at anything with more than two conjugated double bonds, so more than a diene. So as you recall, you have your Markovnikov addition of HBr that forms a carbocation intermediate, and then we get our attack of our bromine in the most substituted position. We see the same thing with the conjugated double bond, but we see two different products. Now we've seen something similar to this with our Lilith bromination, but in that case we were going through the radical there. So where is these two main products coming from? Well, when we get the attack, our most stable carbocation will be the one in conjugation, bless you, with the double bond. No matter which substitution that positive charge is, it's going to be more stable if it's in conjugation with the double bond, even if there's a tertiary one available. But when it's in conjugated with the double bond, then we have our resonance structure, which makes that positive charge the most stable. So in this resonance structure, remember, we don't have an interconverting structure, but we have an average where the positive charge is on this carbon and on this carbon. Now, one of these can be attacked by the bromine, forming our two possible products. Now, this particular carbocation would not be stable because it's not in conjugation. Now, in this case, it's primary, so we know secondary would be more stable. But if this position was tertiary, it still wouldn't be more stable because resonance stabilization is more stable than induction from it being primary, secondary, or tertiary. So resonance would always be more stable. So our two possible products come from crudely showing the attack on either of those carbons that have the positive charge. Now remember, again, this isn't an interconverting structure. Both of these carbons have a lot of positive charge. But the transition state is different if our bromine attacks the more substituted carbon versus the least in this case. But we can form these two possible products. So we call this the 1,2 adduct because the hydrogen adds in position 1 and the bromine adds in position 2. And typically this is called the 1,4 adduct because the hydrogen's on position 1, but the bromine's on position 4, if we just number those carbons. So those two different adducts are just a common way that we call those, 1,4 and 1,2. And it's descriptive of which carbons the addition occurs in. 1,2 is different from 1,4 in this case because in our 1,2 adduct, our carbocation is the most stable, it's secondary, but our double bond is not as stable as the 1,4 adduct. Remember, our more substituted double bond is more stable. And conversely, in the 1,4 adduct, we're going through a higher energy transition state, but we're forming a more stable product. So we're going to be really looking at thermodynamic and kinetic control to control getting one of these products over the other product. But right now, let's just look at predicting all possible products of this reaction. So again, we're only ever going to look at a diene. We're not going to look at anything more. This gets more complicated for a conjugated triene and a conjugated tetraene, clearly, and that's going to give you too many possible products. So this is really only useful for a diene. So our first step is identify our possible addition places where addition can occur. So of course it can only occur in one of the carbons of the double bond. Based on our locations, let's say the hydrogen added to carbon 2, then our positive charge would not be in conjugation, so that would not form. That would be too high in energy. So we have no resonance structures there. Even though it's secondary, that's irrelevant because resonance is more stable. Same thing if our hydrogen adds on carbon 3. Even though it's secondary, even if that had been tertiary, that's unlikely because the carbocation is not stable as for resonance. So don't look at these any further. They're really not necessary. So if our hydrogen adds on carbon 1, we do have resonance stabilization, and both of these can lead to a product of our bromine adding to those two carbons. Also, if our hydrogen added to carbon 4, we also form resonance stabilized. So we have to consider all 4 of these intermediate carbocations. And remember, we don't have interconverting structures for resonance, but we can crudely think about it that way. So comparing all of those, our bromine can attack for those positions, and looking at these. Now, note, these two products are the same, so we do not need to draw them twice. So really, we're only going to form 3 distinct products, not 4 distinct products, because those two products are the same thing. If we were to put this in space, like this, it's the same compound. You would know that also by if you named it, it would have the same name. So those two compounds are the same. I don't want to see them drawn twice. So really, our answer would be those 3 possible products. Again, we're not looking at control at this point. We're just looking at the possible products. The other thing we haven't discussed is, of course, chirality. That's also something we need to consider. So if we look at this example, our stereocenter is produced. We're going to form both enantiomers, just like before. So in these examples, and by before I mean our other addition, HBr reactions, because we're going through a carbocation. So because we have this as a stereocenter, we get both enantiomers. This is a stereocenter, we get both enantiomers, and this is also a stereocenter. So we would, of course, get both enantiomers for all 3 of those products. So we'd actually get 6 products if we're not controlling based on temperature, which we're going to talk about control next. So looking at this example, our possible products, we can get, again, you can go through these, but the addition of hydrogen on carbon 2 or carbon 3 will lead to carbocations that are not in resonance. So we're not even going to look at those. And they're not resonance stabilized, we're not going to get those additions. So we can get the hydrogen added to carbon 2, and we can get this possible 1,2 addition. We can get this 1,4 addition. And in this case, our 1,2 addition and our 1,4 addition is the same. So we don't necessarily need to draw those separately. We can also get, our carbon adding to this one, and we get the 1,2 addition from that carbocation and the 1,4. So we would get these 3 products. Again, these 2 are the same exact product. They're the exact same thing. If you were to name them, you'd have the same name, so we do not need to draw them separately. Now notice this particular product doesn't have a stereocenter, so we don't need to specify an enantiomer because it doesn't have a stereocenter, but these do have a stereocenter. So looking at this one, our distinct products that will form is actually 3 distinct products. Here are our possible products depending on where our hydrogen adds. And I'm showing the hydrogen to be really clear. So here's our 1,2 addition if hydrogen adds on this carbon. Here's our 1,4 addition if hydrogen adds on this carbon. If hydrogen adds here, here's our 1,2, here's our 1,4. So that's our 4 possible products. But these 2 are the same product. I'm showing the hydrogen, but remember there's hydrogens here as well. I'm just showing the hydrogen that added from the outside source. So since those 2 are the same product, we actually only get 3 different products, ignoring stereochemistry. Of course, this isn't a stereocenter, so we wouldn't have to worry about that. And this isn't a stereocenter, but we would get both stereocenters for that particular one. But I specified to ignore stereochemistry for that one. Again, you won't get the hydrogen adding on carbon 2 or 3 because that carbocation that forms would not be in resonance. So that would not be a product that you would get. So this particular reaction is not very useful unless if we control the fact that we're likely to get at least 4 products, if not 3 products if we get 2 of the same. So we need to get a little bit more into selectivity, and we can do that with temperature. we talked about the fact that we have the 1,2 adduct and the 1,4, and the way the book talks about 1,2 and 1,4 adduct, I want you to be clear. You have to look at all of your examples. Depending on what your compound looks like, this might not necessarily always be true of the 1,2 and the 1,4 adduct. Instead, what we're going to do is just compare the carbocation and the product. But in this case, the 1,2 adduct goes through a lower energy transition state than the 1,4 adduct, and in this case, the 1,4 adduct is the lower energy product. So what we see is at 0 degrees Celsius, we get mostly the 1,2 adduct, and at 40 degrees Celsius, we can select the 1,4 adduct in this example. So what's going on here? That brings us back to chapter 6 with thermodynamic and kinetic control. Oftentimes, thermodynamic and kinetic control is the same product. The lower energy transition state will often lead to the lower energy product. But that's not the case in this example. In this example, the lower energy transition state would form this product, but the lower energy product is this one because the double bond is more stable. So with that, we can actually use temperature to control forming the 1,4, or forming the thermodynamic product versus the kinetic product. So let's look at that based on the thermal heat diagram. Now the first step is irrelevant in this because the addition of the hydrogen to the diene is going to go through the same transition state because we're forming the carbocation. The difference is the transition state once we attack. So when the nucleophile attacks the least substituted positive charge, or the carbon from the resin structure that is least substituted, that's going to lead to the formation of this transition state. And this transition state is going to be higher in energy, because the carbocation isn't as stable. But if we attack the more substituted positive charge, then that's going to be a lower energy transition state. So that's going to lead to and remember, when we're talking about the kinetic product, we're talking about the product that comes from the lower activation energy. When we're talking about the thermodynamic product, we're always talking about the product with the lower energy completely. So when we compare this, kinetically, this particular product is going to form. So if we keep our temperature low, then we can form this product. Again, don't memorize 1, 2, 1, 4, but look at your carbocations. At higher temperature, however, we can get over both of those transition states equally. So if we can get over both of those transition states equally, we're always going to form the more stable product. So at higher temperatures, we form the more stable product, and what we do to look at stability of the product, which is a more stable double bond. So the more stable double bond will be the double bond that's more substituted. Remember, the more substitution, the more stable, because the alkyl halide part is about equal. So the driving force of stability between our products is this double bond is more substituted, this one's least substituted. So at higher energy, at higher temperature, you're going to form the product that has the most substituted double bond. At lower temperatures, you're going to form the product that comes from the most stable intermediate, the lowest energy intermediate. And this is nice. This means that we can select which products we're going to form based on using temperature. If our thermodynamic and kinetic product were the same, then we couldn't do this. We'd only ever get that thermodynamic product. But here we can. So our thermodynamic product is, in this case, our more substituted double bond, but our kinetic product comes from the lower activation energy, and that is stemmed from our carbocation intermediate. So let's look at an example at 40 degrees Celsius and 0. Now remember, this is addition, and addition we got to keep temperatures low because elimination is favored at higher temperatures. So typically, even the higher temperature won't be really above 40, 50 degrees, but that's still high enough to get over both activation energies. But typically at 10, 20 to 0 degrees Celsius, we're only going to be able to get over the lower energy transition state. And in the lab, you might have to play around with these temperatures slightly till you get a huge enough difference in yield for this to be available. So this is just in general, but every reactant, you would have to optimize your temperatures in the lab. So this is an exact amount. You might actually have to do this at 10 degrees Celsius, it depends. So each reactant, you'd have to spend some time in the lab to figure out the best temperature. So if we look at 40 degrees Celsius, first off, if our hydrogen adds on carbon 1, these are our possible intermediates. So our resonance structures. Also, we have to consider if our hydrogen adds on carbon 4. And these are intermediates. So the first thing we need to do is consider all our intermediates and all products that form from them. So once we do that, then we can go further. So this is the same steps we did before. Notice we have the higher temperature here. So what we're going to form is our lowest energy product. It's going to be favored, so that'll be our major. That doesn't mean we won't form some of the other products, but we'll form that as our major product. We'll likely still have to do some separation techniques. So what we see is we look at the double bond for this. We have a tri-substituted double bond. Here we have di-substituted. Here we have mono-substituted. And here we have di-substituted. Our most stable double bond is the most substituted. In this case, we have a tri-substituted double bond. So that will lead to our major product at higher temperatures. And of course, this is a stereocenter, so plus and anti. Now that doesn't mean we won't form any of the other ones. We'd likely still form a decent amount of these two di-substituted, but we would expect tri-substituted to be major. Now at 0 degrees Celsius, our lowest energy transition state is going to be favored. So now we can look at our carbocation. We're going through a secondary carbocation through this one. This one's a tertiary, this one's a secondary, and this one's a primary. Our most stable carbocation would be from this tertiary, so that would lead to our most major product under lower temperatures, because that's the activation energy we'll go over. Now if we have a case where we have two possible products that can be from tertiary, they're both going to form. Now remember, this is tertiary and under resonance. We're never going to form the product where the carbocation was not in resonance, because that's not stable enough. That would be a higher transition state. So in all cases, we will not form that. We're only going to go through intermediates where the carbocation is in resonance, because resonance is more stable than induction. And we talked about that when we talked about acidity and aerial. Resonance is the most stable, so that's what we'll be looking at the most. So that's what we're looking at. Temperature absolutely makes a difference. If no temperature is noted, you're going to form all distinct products. But in this case, temperature is specified. So higher temperatures, we can get over all transition states. So therefore, we're going to form the most stable product, which is going to be the most substituted double bond. At lower temperatures, we're only going to be able to get over the lowest energy transition state, so that is stemming from our carbocation. So looking at this example, we see we're doing 50 degrees Celsius, so that's at that higher temperature end. Now this is doing BR2, but that's fine, because again, that's going through the carbocation. So it's the same discussion with that case. Whether we're talking about HBr or BR2 can go through the same concepts. We have that resonance stability. But under higher temperatures, we're going to form the product from the most stable double bond. So in this case, both B and C are tri-substituted, so we'd expect to form both. Because neither is more stable over the other. They both have the same amount of substitution. So we would expect to form those two. But I'm mostly doing the stick with HBr for y'all. A is not a possible product, by the way, because this is showing one of the bromines adding to carbon 1. Carbon 1 does not have a double bond. That's an sp3 carbon. There's no functionality at that carbon. So A cannot be the answer. Just keep that in mind. Oh, my X. now that we talked about that, the next part of this discussion will be, and the rest of this chapter is going to be pericyclic reactions. So we're going to talk about what a pericyclic reaction are. They're very specific. There's 4 general features to determine a pericyclic reaction over anything else. 1, the reaction mechanism is conserved. It all happens in one step. There's never any high energy intermediates. If I give you a pericyclic reaction mechanism, this should be the simplest mechanism you've ever done, because all you have to do is put the arrows in the starting material. Because it's concerted, it all happens at once. It proceeds without intermediates. This is literally the mechanism. Those 3 arrows is all you need to draw. Do not draw intermediates, do not draw positive charges. If I give you this mechanism, that's all I want are those red arrows. I will not give any partial credit for this question. This should be the easiest mechanism you do. I don't want to see any intermediates. There's never any intermediates in these reactions. That's what's specifically one of the main features of these reactions, is no intermediates formed. So the reaction happens all at once. It's concerted. The mechanism always involves a ring of electrons moving in a closed loop. Notice, this is a closed loop of electrons. Electrons forming a bond. This bond's breaking, this bond's forming. This is a closed loop of electrons. That's how your mechanism always looks. It should be the simplest mechanism question I asked you. The transition state is always cyclic. Now remember, the transition state we don't typically draw in the mechanism, but that helps us with predicting our activation energy. And the polarity of the solvent does not affect the reaction rate. Why does the polarity of the solvent not affect the reaction rate? Because we do not form any intermediates. The polarity of the solvent only affects the reaction rate when we form a charged transition state or a charged intermediate. We're not forming any positive or negative charge, so whether our solvent is partial positive or partial negative will not affect the rate of the reaction. In typical organic reactions, most of them that we've discussed, like the HBr reaction we were just looking at, a polar solvent can help stabilize the transition state by stabilizing the carbocation it forms, lowering that activation energy. We don't see that here, which is one of the reasons that we know that no charged intermediates form, no charged transition states form. We don't form any positive or negative charge. And remember, we can measure that, positive and negative charge buildup. So we don't see that. That's really significant. That tells us that, and we'll often use solvents for these, but the solvent will not affect the reaction rate. Now, sometimes some of these reactions can be done in the solid state, which is the absence of solvent, but most of the time these are done in solid systems. So there's 3 main types of pericyclic reactions we're going to be looking at. One is cycloadditions. It's an addition reaction that we're forming a cyclic compound. Hence, cycloaddition. Again, look at the mechanism, exactly the same. There, we're taking, overall, converting 2 pi bonds into 2 sigma bonds. Now, this might involve more or less than 2 pi and 2 sigma bonds. Here, we're actually using 3 pi bonds, but overall, the difference is we're taking 2 of the pi bonds are not in the final product, and we're forming 2 new sigma bonds. In this case, 1 pi bond is formed. So the difference is 2 pi bonds are formed 2 sigma bonds. This is an addition type reaction. Electrocyclic, we have an open compound that forms a cyclic compound. Again, notice the mechanism. Here, overall, we are losing a pi bond and forming a sigma bond. So this might involve multiple pi bonds, multiple sigma bonds, but where overall we started with 1, 2, and not looking at the carbon hydrogens, just ignore those, but 1, 2, 3, 4, 5 sigma bonds, and we end up with 6 sigma bonds in the final product. So that's an addition of 1. We started with 3 pi bonds, we end up with 2. So that's a loss of 1 pi bond. The last one is a rearrangement. Usually we call these sigmatropic rearrangements, and it's a complete rearrangement. We have the same amount of sigma bonds, the same amount of pi bonds in my starting material and my product. My starting material is an open, my product is open. The difference is and it is a reaction, the rearrangement of where the bonds are, between which atoms, where the sigma bonds are. This one has no substitution, but if I were to number this, you see that in the starting material, our pi bonds were between 1 and 2 and 5 and 6, and now our pi bonds are between 2 and 3 and 4 and 5. But my sigma bond was between 3 and 4, now it's 1 and 6. Notice the mechanism. There's no intermediates, it's just these arrows into my starting material. The difference between the addition and the rearrangement, in the addition, we lost 2 overall pi bonds, formed 2 sigma bonds. In the rearrangement, again, no difference in sigma and pi bonds. In the addition, we had 2 starting materials to form 1 cyclic compound. In the rearrangement, we have 1 reactant to 1 product. So no difference. And the sigmatropic rearrangement is the only one where you're not actually forming a ring. But it's still a cyclic transition system, so it's still a paracyclic reaction. So again, this is just a map out of those 3, and you should know the difference and be able to label the difference between a cycloaddition, an electrocyclic, and a sigmatropic. So let's start with cycloaddition. We're going to be looking at that in a lot of detail today. So the first cycloaddition reaction we're going to look at is 4 plus 2 cycloaddition. And we'll discuss where that comes from. And that's our systematic name. The common name for this reaction is the Diels-Alder reaction, which is a named reaction named after the scientists two scientists clearly, that first discovered this reaction and published about it. Honestly, the Diels-Alder is how it's most commonly known. This is a cycloaddition that's overall 4 plus 2. So it can be very useful because it allows the synthetic chemist to quickly build up molecular complexity. We form this 6-membered ring, we can do a lot with it once we form them. So where does the 4 and the 2 come from? You can either think about the electrons or the pi orbitals, but either way, we have our 4 overall, we're forming the 6-membered ring. We're starting with 4 unhybridized p orbitals plus 2 unhybridized p orbitals in the other molecule. Or you can think about the electrons. We're starting with 4 pi electrons in the first molecule and reacting that with 2 pi electrons. So you can think about either of those. Now there may be other carbons in this molecule, but we're only looking at where the reaction's occurring. So that's 4 plus 2. So here's the mechanism. Again, same mechanism, no intermediates, transition state does not have a charge. So what we form is the 6-membered ring, forming a single bond here. Now this X, we're going to talk about what that's got to be in a couple of slides. So this is the main reaction. Notice here, this pi bond breaks to form a sigma bond between these 2 carbons. So typically we show that arrow going in between the 2 carbons because the electrons are not going to be on this carbon, it's going to be between those 2 carbons. But when we form the bond here, that means that one of these bonds have to break. So we have to push this pi bond over, and that's retained in my product. And then again, this would have 5 bonds to carbon, so we have to form this bond between this carbon here using our pi electrons. So that's our second sigma bond that forms. Typically, and this is not relevant usually to, I don't know why I did that. Don't know where that came from. And again, you can see the 4 plus 2. So overall, that's going to form a 6-membered ring. Now, even though it's not relevant when I'm reading your mechanism, usually the first arrow starts at the diene. And we're going to talk about why, and it's based on that X that we're not showing what it is right now. But of course, I can't see which arrow you started with in your mechanism when I'm reading it. It's just going to look like this closed loop. So it's kind of irrelevant. So the arrows can be drawn clockwise or counterclockwise direction, and they're both acceptable as long as you're showing the sigma bonds forming and the pi bond breaking. And this is what our transition state looks like. Again, notice we don't have any charge. So most Diels-Alder reactions are thermodynamically favored at low and moderate temperatures. More sigma bonds and fewer pi bonds equal more stable and lower energy. Now, in this Diels-Alder reaction, notice that we are forming a 6-membered ring. So we don't have a lot of ring strain in the 6-membered ring. So we don't have to worry too much about that. We will look at another cycloaddition that forms a 4-membered ring. But that one has more ring strain. But we don't have any ring strain here. So we're not losing anything by ring strain when we do this reaction. Instead, when we went from a total of 3 pi bonds to only 1 pi bond. So this is going to be lower in energy based on that. Remember, pi bonds are less stable than sigma bonds. So what we see is our Diels-Alder product is typically lower in energy. However, because we have a delta S here of more disorder to less disorder, so we do have a delta S that we have to consider, at higher temperatures, what's called the retro Diels-Alder or the backwards reaction can occur. And you can actually calculate what that temperature is. But it's favored, the backwards reaction happens because of entropy. Entropy favors the retro Diels-Alder because we have more disorder on that side. So at higher temperatures, then again, remember, our delta G is equal to our delta H plus negative T delta S. So therefore, that temperature term is tied with our entropy term. So if we get that entropy term bigger, then we can get the backwards reaction to be favored. So we can actually calculate that pretty easily to figure out what temperature for most retro Diels-Alders are favored. If you know your delta H and your delta S, so if I told you your delta H was negative 40, and I told you your delta S was negative 43, then you just need to find the temperature. Remember, this is Kelvin. It's never in Celsius because we don't want that temperature term to give us a positive or negative. What we see is the higher the temperature, the more the delta G goes to the positive end. So you can actually figure out which temperature you need to get this number to be positive because of that delta S term. There's 2 reactants in the Diels-Alder reaction. We have our diene. That's pretty straightforward. That's a compound with 2 enes. So the compound with our 2 double bonds that are in conjugation. And then we have the other compound, which is our dienophile. So that's what we call it. It's the thing that loves the diene. Hence dienophile. So it's what's going to react with the diene. So it's basically just a compound that has a double bond. But in the Diels-Alder reaction, that's what we call it. If a dienophile is not substituted with an electron withdrawing group, then typically it takes too much energy for the forward reaction to be favored. So if there's nothing here, then we require high temperatures, but high temperatures doesn't really favor the Diels-Alder reaction very well, because we just looked at that. The higher temperatures favor the retro. So what we need to do is make this more accepting to the dienes electrons. So what we can do is put electron withdrawing groups on the dienophile, and we can lower the reaction temperature and increase the rate. So if we look at this reaction, our product, here's our mechanism. It's what our mechanism always looks like. Also note, oxygen is not going to accept the electron. This is our electron withdrawing group. So ignore that double bond. The reaction's happening at this double bond. The carbon-carbon double bond is where the diene is our dienophile. So this is our electron withdrawing group to make our reaction occur in a faster rate. So our mechanism is just going to be this, and we're forming a new sigma bond between carbon 4 and 5 and carbon 1 and 6. And notice the only double bond that we're going to retain is the one between 2 and 3. A has 2 double bonds, so that's not going to happen. Also, we lost this methyl group. That methyl group's not going anywhere. So A is not a possible product. D, if we had this, we would have to have hydrogens leave. Because notice, there's 2 hydrogens in carbon 4. Here, there would only be 1. Hydrogens are not the leaving group, so that won't occur. So, and this one, again, carbon 5 has 2 hydrogens. This carbon only has 1 hydrogen. Notice here, carbon 5 has 2 hydrogens, and it has 2 hydrogens there. You can draw in your hydrogens. You're not losing any hydrogens in this reaction. You're not losing any carbons. All you're doing is losing 2 pi bonds and forming 2 new sigma bonds. So that's our product. So electron withdrawing groups, bless you, are attached to our dienophiles to make the reaction happen quicker. So here's some examples of electron withdrawing groups on our dienophiles. These are groups that have a carbon separating an electronegative atom. Because electronegative atoms will pull electron density away from our double bond and therefore make it more reactive. Also, all of these have resonance structures that give us a positive charge on one of the carbons. That makes that carbon very electrophilic. So that increases the ability of the diene to attack one of the carbons to form that first sigma bond. Now remember, this happens all at once. So as soon as the first bond happens, it continues to occur. But this shows why we get the attack on the carbon. Notice we would not get the attack on the oxygen because that already has a negative charge in that resonance structure. So any of these that have a carbon with a electron withdrawing group next to it, those are all really good electron withdrawing overall groups. So we have these electronegative. Now clearly if we were looking at reactivity, these two would probably react more than this one, because this one only has 1 oxygen that's electronegative. These have 2 oxygens that are electronegative. So you can imagine that we would have an even faster rate with this versus this. And then the cyanide, C triple bond N, again, you get that one. You get that resonance structure. So electron withdrawing groups, and we typically draw them on the dienophile to make the reaction go forward. The next thing we need to discuss is stereochemistry. The main thing to remember is this reaction is concerted. Bless you. So, the Nicella reaction is stereospecific depending on what your what your dienophile starts with. So if your dienophile starts E or trans, then you're going to form the trans product. Fairly straightforward. Remember, this is concerted, so we do not have free rotation around this bond. So that means while the reaction is occurring, there's no free rotation because the reaction occurs all at once. If we start cis, our final product is going to be cis. So that's fairly straightforward as far as what you're going to get for your products. So looking here, we're starting trans, so our answer will be trans. Note with this one, this bond is still there in the final product. Just because it's there, it doesn't react, so it's still connected to carbons 1 and 4. The main reaction is still there, no matter what's attached to the diene, no matter what's attached to the dienophile. The only reaction that's happening is between these 6 carbons. So whatever else is attached there is still attached there in the final product. So that's what's wrong with D and B. Those 2 carbons are not still there. A, they are, but we wouldn't get the cis product because we're starting with a trans double bond. Now, we can actually, I don't know why it does that. We can actually ignore the numbers. Start with a triple bond for our dienophile. Now notice we only use 1 pi bond in the reaction, so that means we do retain the double bond there. Because we're only using 1 pi bond. This is the exact same reaction, the exact same mechanism, but we're left with a double bond because we're only using 1 of the pi bonds. That's 2 pi. So we're only showing the breaking of 1 pi bond, so we retain 2. If I do this and I want you to draw your starting material, you need to recognize that we started with a triple bond because we have a pi bond there. So if we only have double bonds, we're only going to end up with 1 double bond in the final product. But if we start with the triple bond, then we're going to retain that. So let's look at an example. So here, again, the things attached to the diene and the dienophile are still going to be attached in the final product. So here we have our diene in green, our dienophile is in purple, and in red is our electron withdrawing group. Now you can have carbons, which are electron donating groups, on the dienophile, but typically we try to put the electron donating groups on the diene because it's the one that's first starting the reaction. So notice all the R groups that were attached in the starting material are attached in the final product. We did form 1 stereocenter here, but notice this is a pi bond, so we're retaining the fact that where it is. There's no stereocenter here. Here's our new bonds. So we're going to get both of these enantiomers because we don't know how this pi bond originally interacted. They can come from both faces. If we look at this one, we have 2 pi bonds that are left over, which means we must be starting with a triple bond because we have the 2 pi bonds total. So we're going to be having the diene and the dienophile, but in this case, it's hard to tell which one's which. But there is a way we can tell which is the dienophile, and that's because the electron withdrawing group should be attached to our dienophile, which are 2 carbons with the pi bond in between. So here's our electron withdrawing group, which means that must be our 2 carbons of our dienophile here. And since we have a double bond, that means we have to start with a triple bond. So once we find our electron withdrawing group, we know these are the 2 new bonds formed, and we can draw our diene and our dienophile. Typically, again, our diene will have our electron donating groups on it, but that's not always the case. What is always going to be the case is our electron withdrawing group is going to be on the diene. If we only end up with 1 double bond, clearly those 2 carbons were part of the diene. But if we end up with 2 double bonds, we have to find our electron withdrawing group, because that's always on the dienophile. So we can't actually do the retro-Diels-Alder. Diels-Alder reactions can be affected by the diene structure. So remember we talked about this S-cis and S-trans. Well, for the Diels-Alder reaction, the diene has to be in the S-cis form. In fact, it can only occur in the S-cis form because, again, that mechanism is concerted. So those pi electrons have to be in that S-cis form so we can form that six-membered ring. So if we look at this example where our diene is stuck in the S-trans form because of this ring, what we see is no reaction is going to occur. There's no way, because of the ring system, that we can have rotation to form the S-cis because this ring is holding it there. We don't have free rotation around the carbons in the ring. So we don't get any reaction because we can't be in the S-cis. We can only be in S-trans. Conversely, if we have a compound like cyclopentadiene that is stuck in the S-cis, that's going to be very reactive. And in fact, cyclopentadiene will often, at room temperature, react with another molecule of itself to form this Diels-Alder reaction. So you have to be careful with cyclopentadiene that that's not occurring in solution or in its full in its bottom. So we get really quick reactions if we start with cyclopentadiene. Now notice, if we're starting with cyclopentadiene or our diene in the six-membered ring as well, but what we see the most is in the five-membered ring, we're still going to have that bridge that's still going to be attached to carbons 1 and 4. So there's 4 possible products that can form, but of course these 2 are not possible because we started with the cis. So we can't form our trans product. So because of, in this case, we're starting with the cis dienophile, we can only form the 2 possible products where our groups are cis. So these 2 are trans, they're impossible. We're not going to see that because of what we're starting with. Now if we started with the E, then we could form those 2. So with that bridgehead, the question is, will we get mostly product where our 2 electron withdrawing groups are on the same side as that bridge or on opposite sides? And that's what we're going to look at. So for bicyclic systems that form like this, and again, those groups are still on there, there's 2 possible groups that can form, an endo product and an exo product. And that just describes where the functional groups are. So it's based on the bigger bridge. This has 2 carbons, this has 1. So this is our larger bridge. So the endo product is syn to the larger bridge. So that would be this guy. The exo product is anti to the larger bridge, or on the same side as the smaller bridge. So that would be this example. So the question is, which is more likely to form? And we have to look at the transition state. Now, if we look at these 2, one substituent is endo, and one substituent is exo, so we form both in that case. But if we only have one substituent and we form a bridgehead, and this is only relevant when we have a bridgehead. This isn't relevant if we don't form a bicyclic system, the Diels-Alder. So the question is, what's more likely to form? And to look at that, we have to look at the transition state. So we have our Diels-Alder coming together. And we're looking at this, and the question is, what's more likely to form? So what's more likely to form is there's a favorable interaction between our developing pi bond with our electron withdrawing groups, or on this side, because of the fact that they are electron withdrawing groups. So this is a kinetic argument. We're going to have a lower transition state if our 2 electron withdrawing groups are interacting with the developing pi bond. That's going to lead to the 2 electron withdrawing groups being on the same side as the bigger bridge, because that's the one where the developing pi bond is. And it has to do with the fact that they are attracting those electrons there. So basically, this is a kinetic product. We're going to have a lower transition state. Thermodynamically, you might expect the substituents to be on the side with the smaller bridgehead. So this is a kinetic product. So that's what we see. We're going to form the endo product if only the endo product forms. Like I said, in this case, one substituent's endo and one's exo, so we form both of them, because that's true in those two. But we wouldn't get that in starting with the Z, only if we start with the E. And again, this is only relevant when we have a bridgehead. So your electron withdrawing groups are on the same side as the developing pi bond. Let's look at this in the molecular orbital level. We drew these molecular orbitals, you should be able to draw them. So we're doing the reaction between butadiene, these are our molecular orbitals, here's our HOMO and LUMO, you should be able to draw these. And if you don't know how yet, you need to practice them over the break, because you will be tested on drawing these. And then it's reacting between ethylene. So that's just our dienophile. Now again, we can have electron withdrawing groups, we can have R groups, it's not going to change this. This is always our molecular orbital diagram for the Diels-Alder reaction. Because we are not drawing the R groups that are attached, we're only representing the unhybridized p orbitals and that 6 pi electron system. So it doesn't matter if there's 50 CH3 groups attached to this compound, this is always going to be what our diagram looks like for a 4+2 cycloaddition reaction. And we only have a total of 6 pi electrons. So what's going on this level? Well, what's going on to start off the reaction is the HOMO of the diene has to donate electrons to the LUMO of the dienophile. That's why our dienophile works better when we have electron withdrawing groups as part of it. So what has to happen is those two orbitals are what we're going to look at. Now, to form our new sigma bonds, what has to happen is our LUMO of our ethylene p orbitals have to interact with our in-group p orbitals of our butadiene. Now remember, we retain this pi bond, so those two hybridized p orbitals are still in the product. But these two unhybridized p orbitals are not in the product, and instead we form those sp3 overlap. So to get this reaction to occur, our HOMO of our butadiene in-group orbitals and our LUMO of our ethylene in-group orbitals have to match to get this desired overlap. So under heat conditions, this can occur. And we're going to look at in the next, starting with on Monday, and then we're going to finish up this chapter, because we spend the most time on the Diels-Alder and the cycloaddition reactions. We're going to look at the fact that the 2+2 cycloaddition, again, notice same mechanism, doesn't interact in the same conditions. It doesn't work for the conditions that we're looking at with the Diels-Alder. Have a good fall break. I will see you on Monday. We will finish up this chapter. Have a great day. Thank you. Have a good day. You too. Thank you.
Are you going to be around like for the next hour or two?
I have class at 4 p.m.
Okay.
If you're turning in your things, you can turn it in to
At the-
my box in my in the main office.
Okay.
There's a mailbox in there.
Thank you.
You too. You as well.